So what we're going to be looking at inside of this video is we're going to be looking at parametric surfaces. The reason why we want to look at parametric surfaces is because we're going to be doing the equivalent of line integrals, but we're going to be looking at them from the perspective of surfaces, right? So if you think about what a line integral is basically it's the value over a vector field for a curve, right? Okay, and that curve is one-dimensional. Right? Okay, so you've got the curve, then we kind of imagine that we got this vector field, right? And then we kind of evaluate that vector field over the curve. Well, what happens if we say, for example, we have a three-dimensional vector field now, and what we're going to have is we're going to have an entire surface, so something that has area now in that vector field, okay? Well, then we're going to need some way to go out and figure out what the value is for what we're going to call that surface integral. And in order to do that, we're going to need a parametrization of the surface. So we're going to need to be able to parametrize the surface. Before, with the line integral, we just parametrize the curve, and we know how to do that. We know how to do that in three-dimensional space. Now we need some way to parametrize a surface, okay, to think about surfaces, all right, so that we can go out and find those surface integrals, which are our area equivalent of line integrals. So we're going to begin by stating that a parametric surface is going to be given by a description, and it'll be r of uv, so it's a vector, and that's equal to x of uv, y of uv, z of uv. So what we notice is that we're going to have our x component, a y component, a z component, and each one of those components is going to be parametrized in terms of u and in terms of v. Okay, and so if you kind of think about this makes sense, given the fact that we're looking in three dimensions, so we need to make sure that our parametrization has two variables, all right, to go along with this r, which is our dependent variable. The second part of the parametric surface is this parameter domain, and that's the set of points that can be substituted in for u and v. We're going to define what those points are. In general, oftentimes when we think about a domain, we think to ourselves, okay, so these are all the possible points that we can plug into our equation that will actually give us an answer. So like not all the ones that make it undefined. Well, in the case of the parameter domain, what we're going to think about it's like the value t inside of, say, for example, a line or inside of a curve. It says, okay, I'm going to follow this curve from this endpoint to this endpoint. Well, what we're going to do now is we're going to define u and v, okay, in order to tell me like where do I start my u's, where do I stop my u's, where do I start my v's, where do I stop my v's. So to give you an example of that, let's say for example I have r of uv, and we're going to set this equal to, it's going to be cosine u, sine u, and v, okay? And just to tell you, we'll talk a little bit more about how I know, but if I actually just said, all right, any value for u and v that I want, then what I'm going to get here is I'm going to get a circle of radius 1, and it's going to be a cylinder, actually, pardon me. It's going to be a cylinder. We're going to have these circles moving up and down the z-axis, okay? But if I actually were to restrict the domain, say u less than or equal to 0, less than 2 pi, and I were to say that v was greater than or equal to 0 and less than or equal to 6, now what I have is I'm going to have a cylinder, right? Again, because we're going from 0 to 2 pi for my u, okay, we'll have the full circle, but the cylinder is only going to go from the z equals 0 plane to the z equals 6 plane, because that's our value for v, okay? So this actually kind of constrains what our parametric surface is going to look like. All right, so now in order to help us understand parametric surfaces a bit better and be able to draw them and to visualize them, let's first talk about grid curves. So a grid curve is going to be the description of a parametric surface if we hold one of our variables, either u or v, as a constant. So let's take a look at that last example. So remember we had r of uv, and it was ended up equaling cosine u, cosine v, or excuse me, sine v, sine u, excuse me, v. Now, suppose that what I do is I let u equal, and let's choose let u equal 0. Okay, so if I let u equal 0, then what I get is I get the point 1, 0, and then v. So I've got this line in space my x value is 1, my y value is 0, and essentially v can be any value that I want. So all I've got there is I've got this straight line. I've got the line in space, okay, at that point. If on the other hand, I let, say for example, v equals 0, then r of u, in this case call it 0, is going to equal cosine u, sine u, and 0. And so what we get there is we're going to end up getting a circle on the z equals 0 plane or on that xy plane. So it ends up being a circle, right? Because cosine squared u plus sine squared u. So you get the unit circle, right? So there's a radius of 1 on that plane. So those two grid curves, when we put them together, what you'll see is that if I choose any value for u that I want, right? Anywhere I want, I'm going to get lines coming out, but those lines are only going to be on this circle, okay? Conversely, if I pick a value for v, right, say v equals 5, I'm now going to have a circle up at v equals 5 at the top there, okay? So what we can do is we can put the two of those together and see that what we're going to get is a cylinder. We're going to kind of, sometimes I imagine that what I'm doing is I'm kind of shading in that the lines that are circling the circles, and that kind of gives me that cylinder, right? So putting the grid curves together, we get a cylinder of radius 1. And that's what that looks like, okay? So the grid curves can be actually very informative for us in order to understand what the parametric surface is looking like. Let's take a look at another example. Let's suppose I have RUV and that equals 2 cosine V, 2 sine U, V. So we'll start out with some grid curves. And so I'm going to let U, let's let U equal 0. Okay, that's cosine U, just so it's clear. And so consequently what we get is we're going to get 2, 0, and V. And so you can imagine what we have here in our XYZ plane. We're going to go out to 2, 0 now, and I'm basically going to have a line again. Okay, we're going to have that, in this case, vertical line, right, that extends out at 2, 0, V. If I actually consider a different one, let's say I choose another one, just sometimes it helps me to kind of think of multiple points. We'll let U equal now, let's say, pi over 4. Okay, we'll take pi over 4. And so what we get is we get 2 root 2 over 2, or just root 2, and also root 2 again for 2 sine u, root 2, and then we're going to have a v. And so essentially what we'll get now is we'll get something over in this region right about here, and again we're going to get a vertical line. We get that vertical line there, okay, coming out at that region. Okay, and so this was when u equals 0, and this was u equals pi over 4. Now, let's suppose we let v equal 0. So we'll let v equal 0, make things easy. And so now we have 2 cosine u and 2 sine u and 0. So just to show you, just as a reminder of how this kind of works, since we only have a single variable, we can use all of our other parametrization techniques that we had before. So if you remember, with something like this, if I take 2 cosine u squared plus 2 sine u squared, okay, that's going to end up equaling 4 cosine squared u plus 4 sine squared u, okay, and so essentially what we're going to get is we're going to get 4 times 1, okay. And so basically what we've got here is we've got a circle of radius 2, circle of radius 2, okay. This thing here, that ends up being the radius, that's r, okay. The cosine, that has to do with our x variable, the sine ends up having to be our y variable, okay. And so consequently what we get here is we get a circle of radius 2 in that xy plane. Pick a different value for z. If we pick a different value for z, we're now going to go up into the whatever plane that is, let's say for example that's z equals 5, that's going to be then v equals 5, okay? And we'll get that circle. It's still a circle of radius 2, okay? So what our surface is, you can see what our surface is now. It's a cylinder of radius 2. With no bounds here, it actually just goes up towards infinity, because what we have is we have that v goes from negative infinity to infinity, and our u goes from 0 to 2 pi. So what we can kind of see here inside of our last two examples is we can find the parametric equation for a cylinder. So our cylinder is going to be r of uv, okay? And that's going to equal, and we're going to call it r. Notice that this is going to be a scalar value, r cosine u, r sine u, and then v, where r is the radius of the cylinder. And then we can constrain how that cylinder is going to look based upon by taking our domain, okay? So like for example, and how we might write our domain, right, is d equals the set u and v, such that u is greater than or equal to 0, less than or equal to 2 pi, and then v is less than or equal to a, less than or equal to b. So what this would do is that would have the cylinder go between a and b, okay? So like the bottom of the cylinder would be a, the top of the cylinder would be b, all right? And that would be the height of the cylinder would be b minus a. And that's an equation for a cylinder. Let's take a look at another surface, okay? Let's consider this surface here. It's going to be u cosine v, u sine v, and then we'll use u squared, okay? And what we're going to do is we're going to constrain, we're going to say that u, we're going to set u and v, this is going to be our domain, and we're going to let u be greater than or equal to negative infinity and less than or equal to infinity. And then our v, notice that our v is going to be the things that we put into the trigonometric equation. So v is going to be less than or equal to 0 and less than, or excuse me, greater than or equal to 0 and less than or equal to 2 pi, okay? In fact, because we've got the u squared, one of the things that we can do here is we can actually just make this, we're going to make that 0. We're going to go u greater than or equal to 0, less than or equal to infinity, to keep from having any real problems with that. So a couple of things that I want to notice here. Notice that instead of, like in the cylinder example, if we go to the cylinder example, r here, that's constant. In this case, u is changing, okay? As u increases, which means as we go up in the z, because notice that u squared has to do with the z. So as u increases, the size of these gets bigger, okay? Whatever they are, they're going to get larger. The size of u cosine v and u sine v gets larger, okay? Now, you probably say to yourself, like, okay, the grid curves for u cosine v, u sine v, and some constant value of u are going to be circles, and they are going to be circles again. But those circles are going to get progressively larger, okay? They're going to get progressively larger. And so what we're going to do is we're going to hold u constant. So we're going to think about some grid curves, and we're going to hold u constant. And so we've got, right, u cosine v, and then we'll square that, plus u sine v squared, okay, is going to just end up equaling u squared, which, by the way, is z. I can actually rewrite this, and notice that this is x squared plus y squared, a circle of radius u. So a circle of radius u, and that's what's happening. As I move up and down that z axis. On the other hand, if I hold v constant, and this one is, there's a little less danger here, we could just choose, say for example, v equals 0. What we'll get is we're going to get u, 0, and then u squared. So what we're going to get here, right, is we're going to get a line, and I can kind of draw this in space. We're going to get a line, okay, and let's assume that u is positive for the sake. We're going to get u, and it's going to be all the positive values. So it's going to be the positive values of u going upward. Whatever u actually might happen to be. Who knows what that is? And then that's going to correspond at some point in time. There'll be a circle of radius u at the point u. Okay, so this is z equals u, or not z equals u, but z equals u squared, and we get this circle of radius u. The big thing about this, when I'm thinking about this, is to notice that, say for example, if u equals 0, down here, I'm going to get that this whole thing, I'm going to get a circle of radius 0, okay? And my z value is going to end up being 0. So I'm going to be, at this point, I'm going to be at 0, 0, 0. As I increase, right, as I increase u and move around v, what I'm going to do is I'm going to actually increase the width of that circle. So the width of the circle increases as I go up in terms of u, okay? And the height increases by a matter of u squared. So what I end up getting is I end up getting these circles that get bigger and bigger and bigger as I go up the z-axis, okay? Each one being a circle of radius u. So I'm going to go back to this thing right here, right, where I just changed over my parametrization. I took x squared plus y squared, and that ends up equaling u squared. Notice that u squared is z. So I get x squared plus y squared equals z as the equation for my parametric surface. And if you notice that this is a parabola. It's your standard paraboloid, x squared plus y squared equals z. And so an equation of this form, u cosine v, u sine v, u squared, is going to end up being a paraboloid. Okay? So you can kind of see how that parametric surface is constructed using like just this equation right here. Let's take a look at another example. Now let's consider r of uv equal to u cosine v, u sine v, u. And we're going to go u less than negative infinity, less than infinity, and v greater than or equal to 0 and less than 2 pi. So I'm going to look here, I'm going to consider some grid curves, okay? And we'll consider, let's say for example, we'll let u equal 1, okay? So if we let u equal 1, I'm going to get cosine v plus sine v, or cosine v, sine v, 1. And that's going to end up being a circle of radius 1 in the z equals 1 plane, right? We're going to get, right, cosine squared v plus sine squared v equal to, in this case, 1. Okay, so that's a circle, radius 1. Let's say, for example, we let u equal, say u equals 3. Then we get 3 cosine v, 3 sine v, and 3. And so this is a radius of 3, right? It's a circle, radius 3, in the z equals 3 plane. So basically, as we moved up the z-axis, okay, so as we moved up the z-axis, we actually end up getting larger circles, just like our last one, okay? But notice, this is not a u squared. So we're not getting bigger, right? Like, we're not getting taller. We're not doubling the height, right? As we increase u, they're going up at the same rate. Okay, they're going up at the same rate. Also, by the way, though, we notice that u can be between negative infinity and infinity. So, like for example, let's say I use u equals negative 3. Well, u equals negative 3 is still going to be a circle of radius 3. Okay, right? But notice we've got negative 3 cosine v, negative 3 sine v, okay, and negative 3. The big thing here from the perspective of our parametric surface is that this is in the plane z equals negative 3. So now we're actually below, okay, we're below the xy plane, okay, but we've got a circle of the same size. The circle is exactly the same size. I mean, it happens to be circling it in opposite direction, but it's the same size, okay? And so we kind of want to imagine that whatever we've got here is going to look exactly the same above the z equals 0 plane and below it, okay? Above and below, and it's going to get progressively bigger. It's going to get at a ratio of 1 to 1. It's going to get bigger as we expand, right? And they're going to be circles. So let's imagine then that what we do here is we actually, well, we do know, on the other hand, that if we take and we let v now be a constant, we let v be some constant, we're going to end up with something that's going to be u, another constant, or a constant, a constant, a constant, right? So we're going to be going around in a circle, and we're going to have these straight lines again. Okay, so we'll have those straight lines depending upon which one of those large circles that we're at. Okay, so I'm going to kind of visualize this. I'm going to put this into a graph using those pieces of information that I have, and I actually am going to need below z equals 0 this time. Okay. If I'm at actually v equals 0 or z equals 0 plane, you can see here, okay, that at v equals 0, we're going to, or excuse me, at u equals 0, not v equals 0, but u equals 0, we're going to be at the point 0, 0, 0. Okay, 0, 0, 0. And so we're going to go down to that point, that singularity down there at the z equals 0 plane. I'm going to imagine that I've got these circles. I'm going to just draw one of them. I'll have a circle somewhere up here in that plane. I'll have another one equidistant away down here. And then as I move away from the XY plane, those circles get bigger and bigger and bigger, right? Okay. At a constant ratio, by the way. At a constant ratio, and that's the difference between this and the paraboloid. This is not going to be a paraboloid. These are going to be two cones, all right? Or a hyperboloid of one sheet, okay? So we've got two cones stacked on top of each other. One going up into the positive z-axis, and the other one going down into the negative z-axis, okay? And the big difference here is that instead of a u squared, we've just got a u right there. And we are figuring out u from negative infinity to infinity. So that constant ratio, right, that this is u and this is u, okay, that the height and the radius are the same, that's what gives us that cone. All right, let's suppose we want to find a parametrization now. Now what we're given is we're given a curve or we're given a surface, and what we want to do is we want to find that parametrization. So let's say, for example, I want to find the parametrization for the cone x squared plus y squared equals z squared lying on or above the plane z equals -2. So one thing that I'm going to notice, let's say, for example, I plug in -2. I get x squared plus y squared, okay, equals -2 squared, okay, which is x squared plus y squared equals 4, all right? Makes sense that that's going to be a circle of radius 2, all right, and it's going to be on the plane z equals -2. As I change z, okay, as I go up z or down z, the size of the circle or the size of the radius of the cone changes. It gets bigger or it gets smaller, depending upon how close to 0 we're getting, okay? So basically what I'm going to need to do is I'm going to need the radius to be dependent upon the value that I choose for z. So what I'm going to do is I'm going to say, okay, I'm going to let z equal u, okay? And then we know from the work that we just did, then we can let x equal to u cosine v and y equal to u sine v. By the way, you could do the other way around. You could have that x equals u sine v, y equals u cosine v. It would work. It would be fine. All right. But we'd actually get a very different way of going around that surface or moving around the surface. So if I look here, you can kind of see that that's the case, that this is going to give me that cone, okay? And it'll give me this equation. We can plug it back in. U cosine v squared plus u sine v squared ends up equaling u squared, okay? That's x squared plus y squared equals z squared. Now what I'm going to do is I need to actually define my domain. So my r of uv is going to end up equaling u cosine v, u sine v, u. My domain then, D, is going to equal the set uv such that, well, my u's, we'll just have them go, or excuse me, my v's, we're going to have them go from 0 to 2 pi. Actually, let's make that strictly less than. And then my u's are going to be greater than or equal to -2, and then strictly less than infinity, because we don't actually have, we want to know everyone that's above z equals -2. Why is the u the -2? That's because z is equal to -2, and we're going above the plane z equals -2. Okay, So notice that in this case, the V's are basically, there are thetas, okay, and the U's are our Z's. And that's the parametrization for that particular cone. So now let's finish up by talking about finding a parametrization of the half sphere of radius 3 lying above the xy plane. So what we're doing right now is we're actually working with, we've been working with like U and V, which is a standard rectangular parametrization. But a better parametrization for a sphere is actually to do this in spherical, okay? And we know that a sphere of radius 3, so a sphere of radius 3 is one, and we got rho is going to equal, rho ends up equaling 3, okay? And since we're looking above the xy plane, that's going to be phi is going to be greater than or equal to 0 and less than pi over 2, okay? Because we're only looking at it above the xy plane. And then our theta is going to go from 0 to 2 pi, okay? So that's going to be our theta going from 0 to 2 pi. Now, what we can do then is we can let, right, remember we've got x, y, z. That's our equation. So we're going to substitute in our spherical coordinates in for x, y, and z. So we're going to get rho cosine phi, rho cosine theta sine phi, rho sine theta sine phi, and rho cosine phi. We know what rho is. Rho is going to end up equaling 3. So what we can do is we can change this to 3 cosine theta sine phi, 3 sine theta sine phi, and 3 cosine phi. And then we'll let theta and phi be our variables, and so our domain will equal the set theta and phi, okay, such that phi is greater than or equal to 0 and less than pi over 2, and theta is less than or equal to 0, less than 2 pi. Conversely, if we want to change them to u and v, what we could do is we could just change one of these to u and one of them to v. Like we let that u equal u and that equal v, and then we substitute that into here. That becomes u, that becomes v. Or excuse me, other way around. This becomes v, and this becomes u. All right? They're just variables. All right? So what, in order to like parametrize this sphere, the best thing for us to do is actually use spherical, okay? Utilize the values for x, y, and z for spherical, okay? And then use our domain in order to do the work of like restricting that sphere, okay, or restricting the area of that sphere. Let's take a look at something that we've parametrized before and actually kind of discuss what it might look like if we were to parametrize the surface in terms of u and v. Let's say we want to parametrize the plane 5x plus 4y minus 3z equals 2, okay? So the easiest thing for me to do is I'm going to let x equal u and y equal v, okay? So I let x equal u, y equal v, and that actually is a very common thing for us to do when we're parametrizing a plane, okay? And so consequently, I get 5u plus 4v minus 3z equals 2. So if I rewrite that, I'm going to get negative 3z equals 2 minus 5u minus 4v, and then I'll divide by 3. And so z ends up equaling 2 minus 5u minus 4v over 3. And there we are. Okay? And so my parametrization here ends up being u, v, and 2 minus 5u minus 4v over 3. Okay? Generally, planes, that's how we're going to parametrize a plane surface. It's by doing something like that. Okay? Amongst other things, it's just straight linear terms. So it makes things a lot easier when we're actually going to go in and integrate and the like. So how about now a cone with a base radius r and a height h, where r and h are positive constants. So we've got a base radius r, okay, and a height of h, okay. So here's my height h, okay. Let's imagine that's what we've got. We've got h is there, and then I have, here's my radius, okay. That's my base. My base radius is going to end up being r, okay, r. So in order to get this parametrization, we're going to have to get a little bit clever. So what we're going to do is we're going to notice this is a cone, and one of the great things about cones is that the angle here that's made between the top of the cone and the side of the cone is always the same. It's always constant. And so consequently, we basically are going to have a bunch of similar triangles, right? We kind of imagine that I've got, here's R and here's H, and I'm going to have, like, if I imagine I've got a smaller H, we'll call this H smaller, and we'll end up having an R smaller. And so H over R is going to equal HS over RS. That ratio is going to remain exactly the same. So that's going to kind of help us with developing the parameterization for this. So what I'm going to do, though, is I'm going to have to then figure out, in terms of my U and my V, what is going to be my H, my height here. So this is when, if we set this, say for example, in our parametrization, we set our Z equal to U. So we're going to let Z equal to U, or U down there. So basically, we're going to go from 0 up to the height here. Okay? So what that means is that my height, actually, this height right here, is going to end up being H minus U. That's actually going to be the height. As I go up in my Z's, okay, the height is going to get shorter, so we're going to subtract out a piece from each and every, we're going to subtract out the piece-sized U every time as I move upward in the Z direction. So I'm going to plug that into my equation. So that's going to be H minus U over R, and I'm just going to let R be the radius at the bottom. Okay? And so that's going to equal my starting height, whatever my starting height is, H, excuse me, this is going to be my smaller radius, H over my starting radius. So H minus U is this piece right here. My new radius is going to be that piece right there. That's going to be RS, okay? And that's going to equal the full height over R. I now want to figure out what RS is, because RS is going to be variable, okay? And then we're going to end up plugging that back into the equation for our cone, and that's going to give us the entire parametrization. So I'm going to go in, I'm going to cross multiply, I'm getting R times H minus U equals H times RS. So RS is going to equal R times H minus U over H. And so that's my radius at height U. Or at Z equals U, let's say. Z equals U. Okay? So now I can actually plug that into my parametrization. I'm going to get, remember that for my cone, I'm going to have U as my Z, and I'll have, in this case, R, H minus U over H, cosine V, and then R, H minus U over H, sine V, and then U. And that's my parametrization. And then all I've got to do is I've got to define my set U and V such that U is greater than or equal to 0, less than or equal to H, and V is greater than or equal to 0 and less than or equal to 2 pi. And actually, what is strictly less than 2 pi. Okay? So our U now represents my height. It's going to go from 0 up to H, okay? And then the radius is going to be changing. It's going to get shorter and shorter and shorter, right, as we move up in the Z direction. And the reason why this looks so different is because that cone's actually flipped backwards. Remember the other cone that we had was flipped upwards. This one, okay, our radiuses are getting smaller as we move up in the Z direction, and that's actually why you're minus U right there. Okay? All right. So this finishes up our work with parametrizations and finding parametrizations. Hopefully the examples have helped you kind of think through how we think about finding parametrizations and also how we visualize when we're given a parametrization.